Hello and welcome, everyone. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. It is my pleasure to introduce our Riemann and Baketel Fellow for Music, Harry Mairson. Iconic classical stringed instruments from the Italian golden age of violin making are of great cultural, musical, and monetary value. Unfortunately, therefore, access to them is very constrained. To facilitate musicological and organological research, as well as to refine the artisanal maker's mind's eye, access to these precious instruments can be enabled through non-invasive CT scanning and visualization, historically appropriate analytical software, and 2D and 3D printing. While at Radcliffe, Harry has been working on a project called Digital Amati, after Andrea Amati, the 16th century progenitor of Cremonese violin making. The project aims to provide technical information and support to luthiers, musicologists, and organologists as they think about the structure and interpretation of classical stringed instruments. The Digital Amati project merges Harry's interest in computer science and math with his passion for making musical instruments. Harry has balanced a career as theoretical computer scientist with a lifelong interest in making musical instruments. He marks the years of his educational journey by the instrument he made along the way, from working for a harpsichord maker during college to building a clavichord in graduate school, and now making classical bowed stringed instruments. This year, he also finished a violoncello and a viola. Instead of the usual question and answer that follows our public presentation, today we will conclude with a brief concert featuring the newly made violoncello. We hope we'll enjoy it. And now please join me in welcoming Harry Mairson to the podium.
Thank you, Claudia, and to the fellowship staff for your kindness and academic sustenance this year. To you, Claudia, Sharon, Jen, Allison, Kayla, Maria, Jane. This is the last public talk for the year, so my Radcliffe colleagues who are here, I was hoping we could have some thunderous, appreciative academic applause and maybe some screaming. Okay. Thanks also to the Radcliffe. Can I have a minute back for that? We'll see. Thanks also to the Radcliffe Fellows who are here today, and to friends and violin buddies worldwide that I've invited to attend here and on Zoom, and to the Strad magazine for publicizing this presentation online in the violin world. Thank you all for coming. Amelia Tataronis Riemann met Roy Baketel playing piano for his YMCA exercise class. Roy and his wife befriended Amelia and urged her to apply to Radcliffe. She was accepted and won a Radcliffe scholarship, or so she thought. Years after, she learned that her scholarship was actually a gift from the Baketels, who didn't want her to know. Amelia later endowed the Riemann and Baketel Fellowship to honor the couple who loved her and to offer her own support to all things musical. I also owe them my thanks. Many projects this year were grounded in the personal experiences of the speakers. Growing up, I venerated my father's woodworking shop, and his cherished tools are now part of my own workshop. At age 16, I went to a street sale at the Harvard Coop, only steps from where we are right now, and bought for $1 a recording of the Bach Inventions for harpsichord. It was the first time I'd really listened to that music, but I was even more astonished by the sound of the harpsichord. Since then, I've been devoted to making musical instruments. Years later, our younger son Simon and I often read together a book called Music in the Wood, about a luthier named Martin Cornelissen and his making a cello. It inspired Simon to play the cello and me to build one. So here's Opus 0. Look at his fingers. He already knows what he's doing. The bow has a movable frog, which excited our batracologist colleague very much, but I had to explain to him it's a different kind of frog. Anyways, next. Curtis Bryant is a Boston cello maker and a friend of mine who was invited to a Halloween tango costume party and didn't have a thing to wear. So I said, Curtis, I got you covered. Here's Opus 1, a cello I built from start to finish. And here's Opus 4. Simon was the concerto soloist with the Washington, D.C. Chamber Orchestra. He played a cello that I made for him based on the 1700 Stradivari Stauffer-ex Cristiani at the Museo del Violino in Cremona, Italy. That cello is the prototype for my project, which addresses non-invasive museum curatorship and study of classical stringed instruments. I wanted to make a cello, but how? And how were cello outlines and archings designed? Do luthiers actually know about this design history and accompanying design methods, or do they just copy templates they got in school without understanding? How can this information be made more widely known and usable to violin makers, organologists who study musical instruments, and musicologists? How can we learn from these instruments and also protect them, respecting every museum curator's Hippocratic oath? First, do no harm to the collection, yet facilitating access to what we want to know. That's what my project has been about. Developing and teaching the study of stringed instrument design with the assistance of software, building an online digital library of canonical Italian instruments for study and inspiration, and continuing my own artisanal making. This year, for example, I gave technical support to a Cremonese violin maker building a copy of the 1690 Stradivari Barjansky violoncello, most recently played by Julian Lloyd Webber, brother of the well-known composer. This past year, I also finished a viola and a cello with work on their varnishing, which is always, to use technical Italian words, a purgatorio, if not an inferno, for violin makers, followed by the musical setup of soundpost, bridge pegs, and strings. A violin maker once asked me, is your interest in stringed instruments purely academic? And a colleague of his said, no, he's making a cello right now. I made software tools first to help me climb a challenging learning curve, but also to contribute to violin making knowledge and its dissemination. Software and technology risks the worst robotic machination, but at its best, it can be a prosthetic divining tool for enhancing greater artisanal knowledge and individualization. My own making has let me connect almost like an anthropologist with the violin world and what its artisans do. This combination of academic and artisanal, of minding and making, is at the heart of academic investigations of material culture. So at the heart of my project is to build an online digital library of CT, computed tomography images, for about 15 to 20 really famous instruments from the Italian golden age of violin making. And I have this image up here just to show you the detail that's possible. What it is, it's the glue joint where the neck is glued into a block at the top of the cello. So you're looking at something that's like a 1/10 of a millimeter thick, and you can see the glue. You can also see it needs more glue. And I'm not the only nutcase on the planet who wants to do this sort of thing. This is an article in Le Monde from about 2 months ago about the instrument that was played by Niccolò Paganini, the canone, made by Guarneri del Gesù, which was scanned in Grenoble sometime this winter, and they collected 25 terabytes of information about this cello. So that is 42 gig per millimeter of length, including the neck. Okay, it would have been 60 per millimeter if it was just the body. So there are people who are very, very serious about this. I saw this instrument last summer, and I thought, gee, I wonder if I could get that scanned, and someone was way ahead of me. Yeah. Okay, so what is a CT scan? It's kind of like a salami. And inside the salami is a violoncello. And then the salami and the violoncello are cut into thousands of 2D slices, which is the data set. So for this cello, the Cristiani in Cremona, there were about 6,000 slices, about 65 gig. And when you want an image, some particular plane through the cello, it intersects the plane you're interested in with all the ones that are lined up on one axis, grabs the one line of information on them, and reassembles it into a picture. So here's all the little bitty pieces all being assembled from the slices to produce the image that you want. And why do this? Well, I got it in my head that I wanted to build an instrument based on this famous cello at the Museo del Violino in Cremona. And I wanted the most information I could get about it. And my friend Curtis, the tango dancer, when I told him I wanted to go to Cremona and hold the instrument and see it and measure it, said to me very loudly, he said, "They won't let you get within 50 feet of that cello." So I sent him this picture. But the picture took some months of negotiation and making friends to make it and the project possible. So really, access to these Golden Age instruments is really, really restricted because they're so valuable, because they're so expensive, fragile, of great cultural value. And with CT scanning, lots and lots of people can get access to the geometry and design of these instruments and protect them at the same time. There are some people who are very afraid that this digital information, if let out to some factory, is going to allow the mass production of thousands of copies of famous instruments, destroying the artisanal world of violin making. And there are people who really believe this and have screamed it at me, loudly. But I think they're completely wrong. The great value of this data is the cultivation of the mind's eye of the maker. Because to be a great woodworker, to be a great artisan, you have to have fantastic motor skills, but you also need to have an idea in your head about what the thing is that you're trying to do. And it's by looking at old instruments that you get this idea. And you don't want to just copy what is. You want to be able to look at it and think, what was it before? Like meeting a really old person and thinking how beautiful they must have been when they were younger. So with free software that you can get on the internet, you can use visualization tools to look at any aspect of these instruments that you want, anything about the arching. You don't need an MD PhD in radiology. You don't need a PhD in engineering. If you can run Microsoft Word and can press one of about 5 buttons, you can do it. There's dynamic reconstruction of the interior, so almost like a science fiction film. You can walk around the inside of the instrument. You can see all its restoration. All of those little squares are cleats holding the top together. You can see all the patches. You can see the tool marks on the linings. So there's actually more visible than if you had the instrument in front of you. And there are many, many books of measurements, of critical measurements that are required for the modern instruments as they're made now. And you always wonder when you look at these numbers, how much grappa did the guy drink before he took these measurements? 1 glass, 2 glasses, or 3 glasses? When they measured something, when they measured the distance, was it over the curvature of the arch, or was it point to point? But there are measuring tools that go with this software, so if you want to know the distance between the upper eyes and the FO, you can measure it yourself. You don't have to count on anyone. You don't have to assume anything about what anyone else was doing. You've got the avatar, in your hands, and you can do anything you want with it and measure it any way you want. And for those who don't want to use computers or just don't have one around, I've made a full folio of full-size images of this cello that can be measured like you're measuring the original. And the day that it was printed at Fantagrafica in Cremona, I was there with Savino Pedroni with a tape measure, so I could, because I had an 80-centimeter ruler on it, and I had to make sure that the proofs were good to 1/10 of a millimeter so that I knew that it was perfect. Next, from all of the CT data, you can also do a lot of 3D printing. So I have some examples here. This is the cello that I've been talking about, the Stauffer-ex Cristiani. These are 2 Stradivari scrolls. And this is the Messiah. This is in the Ashmolean Museum in Oxford. It's the most famous violin in the world. It's a plastic model of the most famous, so, yeah. Maybe tied with the Niccolò Paganini violin. And so these sorts of things like scrolls were done before with plaster casts. This is the traditional method where you make a negative from the positive. And plaster casts are a bit like first pressing olive oil. You got to know somebody. And then once you know somebody, you can get in line. You want to get to the front of the line, because every time they press the olives, the olive oil isn't as good. So at the beginning, the negative is really good, so you want to get one of those. But every time you make a positive, the negative gets deformed a little. But with STL files, every time is like the first time. So it's absolutely perfect. And these are used in violin-making schools. This is a private violin-making school in Cremona, the Accademia Cremonensis, where my stuff is. And the Museo del Violino now has a new digital content room that opened last summer with another copy of the 3D print of this cello, video of the archings. And I had a lot of email correspondence with Nicolas Gilles, who's over there on the right, about this cello, and he was immensely pleased to be able to basically hold it in his hands. And when you have an arching and put your hands over it like this, you just learn so much about how it's put together. So the original is under glass, but the plastic one is for you to get up close and personal with. Each part can be investigated and measured as if you had the original cello in your hands. So now some words about material culture. So this is a really famous book, but it's not a book about material culture. The cover is about material culture. It's a really famous saltpeter that Benvenuto Cellini made, but the book is about who he loved and fought with and worked for, and his father loved him, and he loved his father, and his father wanted him to be a musician, and he wanted to be a silversmith. And after about the 10th knife fight, you think, okay, I've read enough of this book. It's a social history, okay? This is a book that's really about material culture, about making a double bass, written by two well-known bass makers. So they interviewed this guy, Monsieur Aubert, who was the patron of a bridge-making company that's still very prominent in France. And they said, how did you used to store the maple slips that you make the bridges from? So he says, probably in French, he said, well, we get some wet rabbit poop and pat it down, and then put some straw over it, and then we put the bridge blanks, more straw, more poop. He's actually telling you how to do something, okay? You might not think that's a trade secret, but it's a bigger step forward than the other book. A project that I like very much in academia about material culture is this project, the Making and Knowing project that's run by Pamela Smith at Columbia, where she found a Renaissance manuscript of artisanal recipes for plastering, painting, polishing, and put together a digital online edition with commentary. And she and her group went and tried to repeat all the experiments in the book to see whether they made any sense. And I admire them tremendously for this. So why would a historian of science be interested in this? Because science used to be called natural philosophy. It was an a priori armchair with equations, thinking about the way the world put together. But somewhere along the line, it started to have a bigger and bigger experimental component. And who knew how to do anything? Who knew how to mix chemicals? Who knew how to bend glass? Who knew how to grind lenses? Artisans. So the thesis that Pamela Smith had was that it was artisans who played an important role in providing the experimental component of science. Okay, that's why she would do this. Not to be outdone, the instrument makers have their own Renaissance manuscript of Henri Arnaud of Zwolle with some famous canonical drawings of stringed instruments and keyboard instruments. And he was kind of a sort of Da Vinci-type polymath. And I drew the lute. That was the one that's most interesting to me. And when I did a really careful, computer-aided drawing of the lute, it dawned on me more and more that these instruments weren't just drawn by some artist who was just good at drawing egg-shaped stuff. It was engineered. There was a method. There was a method for everything. Okay? It's not freehand artistry that you're looking at. And even the existence of this lute in this manuscript, I don't know if anybody ever made this lute, but it's almost like it's a miniature study. It's what the computer scientists would call a toy problem. Like, if you're going to geometrically lay out an instrument, in principle, it's going to be like this. Now, for my own material culture story. Last fall was total varnish hell. When I switched the varnish I was using, the new varnish had the consistency of maple syrup and wouldn't go on with my brush. I couldn't control the varnish thinner, and I ended up removing all the varnish with a bottle of Everclear. pictured above, I should have got 2 bottles, one for the cello and one for me. A mess. I've been wedded to the brush always for paint, staining, polyurethane, shellac, varnish, and basting turkeys. Imagine a restaurant where you said, I eat everything with a fork. Then they bring you soup. And you go, okay, I'll put bread in the soup, and the bread will soak up the soup, then I'll stab the bread with the fork. Then the chef comes out and says, what have you done to my soup? I had to give up my brush. But for what? So this problem exists in research always. As it does in romance, you have something that works, but insufficiently. And when you have to give it up, you have nothing. And in that void, you have to find the strength to reach for something new. I tried cosmetic makeup pads to put on the varnish. Still too sticky. It looked like whitecaps at a windy beach. I finally gave in and did something I swore I'd never do. I spread it with my hands, which I previously rejected as chaotic kindergarten finger painting. But it worked. I could mix a lot of color in the varnish with a Muller and glass plate and spread out an incredibly thin coat. The varnish had a really long setup time. I could push it around the wood, the grain lines acted like canals. And pushed cross grain, it spread out evenly. With my hands, I had total control. So here's my material culture lesson. You don't adapt your varnish to your favorite brush. That's backwards. The varnish teaches you how it wants to go on. The material comes first. The utensil comes second. I had to learn that the hard way. What doesn't exist in universities is what I like to think of as the Department of Applied Art History. So imagine you have Vermeer experts in this Department of Applied Art History, and they want to learn everything about Vermeer. They want to write books and monographs and go to conferences and, royal societies and get tenure and the whole shebang. Okay, but there's something else they want to do. They want to know how Vermeer mixed his paints because they want to mix paints the same way. They want to know how he held his brush because they want to hold their brush the same way. They want to paint every bit as good as Vermeer. And then they want to paint better than Vermeer. So step 1 is learn everything you can about Vermeer. So David Hockney wrote this book called Secret Knowledge because he became convinced that in the early Renaissance, painters were just getting too good, too fast at painting. And he decided they must have had some kind of prosthetic technique. They must have had some optical technique. And you can see he's experimenting, as pictured in the cover of that book, with a camera lucida. Okay? And he said, I know how hard it is to paint. Okay? They just got too good at it too fast. You can't climb a learning curve with that velocity. Philip Stedman, a friend of Hockney's, is an architect and art historian in London, and he wrote a book called Vermeer's Camera. And what he did was look at Vermeer's paintings and try to reverse engineer the geometry of Vermeer's studio from the paintings. And he could do it consistently enough that he thought anyone who was just painting by eye, I wouldn't have gotten such consistent statistics about the layout of the studio. And then Tim Jennison, a software nerd in San Antonio who made a lot of money in the computer graphics business, read both of these books, befriended these guys, and bought a storefront in an industrial mall in San Antonio where he built a replica of Vermeer's studio and built a replica virginals, which you can see there. It didn't have a working keyboard, and got his teenage daughter to pose in appropriate clothing there. There's a can of Coca-Cola that you can't see on the other side. And he painted, and then he mixed his own paints, he ground his own lenses, to make the kind of optical techniques optical prosthetics that he thought that Vermeer was using, and used this to paint the famous painting, The Music Lesson. It's in the Royal Collection in London, for which he was absolutely hammered by art historians worldwide who said he was just painting by the numbers, like you did when you were a kid. And he said, of course, I'm a nerd. I'm not an artist. What did you think I was going to do? But now take this prosthetic device and put it in the hands of somebody with real artistic talent. Imagine what they could do. That was the point of his experiment. Okay. So from the Department of Applied Organology, not applied art history, we have books on violin making and restoration, on historical analysis of varnish and contemporary varnish, foundational history of violin making, and even contemporary history, particularly the Italian history of the revival of the violin in the 20th century is all tied up with the birth of fascism. It's a rather amazing story that the two of them would get entangled. And a remarkable book on violin design by François Denis called the Traité de l'Outil, the Violin in the Art of Measurement, where he describes the straight-edge and compass constructions that could have been used that were and commonly understood to design classical stringed instruments. So in 2013, there was this exhibit at the Ashmolean Museum, and the program, the catalog said, what distinguished Cremonese instruments was a geometric formality of design and proportion borrowed from architects, painters, designers, and craftsmen. That's what François' book is about. A compass and straight edge is much more accurate than a ruler, protractor, and all of those measurement things on the right. If you want to mark out the slots on a cello nut, as you can see in that photograph, you don't want to do it with a plastic ruler and a pencil. You want to do it with the pinpoint accuracy of dividers. And also, the language of geometry is a universal language. Half, third, tangent, all that means the same to everybody. But on the other side, you have a Tower of Babel. You have a bunch of people saying to each other in confusion, how many furlongs are there in a fortnight, you know? There's none of that in the world of geometry. So I want to take you briefly through how you might design a stringed instrument using a straight edge and compass. And so what I've picked, and this is a technical poster I did this year of the Messiah, this instrument in the Ashmolean Museum in Oxford. That's the one that I showed you before. And I wanted to start with the data, and I can't say whether we're constructing the design or we're deconstructing what's already there. I get mixed up with the words. And I put a picture of ingredients for a martini there because I wanted this to sound elegant and simple. And you should remember, the way to make a martini is 6 parts gin to 1 part vermouth. That's proportional design. Okay, the martini could have been invented in the Renaissance. So, begin with a square. That's the red square, and the only actual distance you'll see in this whole design is 205 millimeters. You know, that much, and no more. So what that tells you is the height of the top 2 sections of the violin. The sections are called bouts, and the width of the lower section. And then you draw 3 more circles, which you can see up there, and they mark out the heights of each of the bouts, okay? And if you look at the square as 1 by 1, then the proportions are like, you know, √2/2 and the other 2 guys on the other side. And I took this picture out of a book on classical architecture to say the way that historians of architecture analyze classical design of classical architecture is it's out of the same can. It's the same toolkit. It's all proportional. Okay. When you look at the ratios of 1 over √2/2 on the right, and then on the left, and then on the right, 2 minus √2 over √2 minus 1, that's this and this, they're both the square root of 2, which is about 7/5. Okay? So you could lay this out almost like a martini, 7 parts gin to 5 parts vermouth. Okay? But when you look at those fractions, what they really are is they're a vestige that are left from a compass construction. And in the repeated fraction, the 7 to 5 over the length of the instrument and the 7 to 5 over the top 2 parts of the instrument, you're seeing repeated structure. That's part of the aesthetic beauty of the instrument, just like how a Fibonacci spiral has a repetitive function that contributes to its beauty. If you draw a green circle in the middle of the red square, it marks out the width of the middle bout. Okay? And it tells you exactly where the minimum is reached. And if you draw diagonals from the lower left and right-hand corners, upstairs, you get to, through the center of the circle, you get to see what the width of the upper bout is. So now you've got the whole rectilinear structure of the violin marked out. Where are the curves? Well, here's some curves. Draw a big blue circle whose center is in the middle of the upper bout, all the way down to point P down there at the bottom. Okay? And then we have to fit this red circle somehow so that to do the lower left flank, the tangent there. So how do we place that? With some more geometry. But don't solve any equations. Don't think about math. The first time I saw this problem, I thought, I'll write out the equation for a circle, and I'll write out an equation for a line, and I'll solve all the, just screw it, okay? You got a green line and a blue circle, and you want to place the red circle so that it's tangent to the interior of the blue line and to the right of the green line. But don't do any math. Just take the red circle and roll it up and down the green line. And you'll see that the center of the circle draws a yellow line. Now roll it around the interior of the blue circle, and you get a yellow circle. And where the yellow line and the yellow circle intersect, that's where you put the center of your red circle. Okay, so you can solve this problem with a straight edge and compass. You don't have to write down a single equation. And Francois' book is filled with things like this. It's an invitation to make millions of mistakes, and I've made most of them, all right? There's not a screw up that I haven't explored, okay? So instead, I put together what the computer nerds call a domain-specific programming language, which is basically a programmable straight edge and compass, where I could repeat line by line everything that Francois said in his book in code. Then I didn't have to draw anything. And then instead of cursing and redrawing, pick the same viola 3 times in a day, I would just debug my code and it would just run again. I didn't have to do drawing, I just had to do thinking. And what a straight edge and compass will do is it'll let you add, subtract, multiply, divide, and take square roots. Exactly. And that's all you need to design a classical stringed instrument. So let me show you a very simple example. Oh, and before, what else did I write here? Yeah, you're just writing code to describe geometric constructions. That's what the programming language is about, okay? And the straight edge and compass, it's an analog computer. It's almost like a geometric slide rule, and this is the simplest example I can think of to say why it's a good idea. You got 3 points, and you want to find the circle that goes through the 3 points. So the high school math way is drag out the equation for the circle, plug in the 3 points, and you get 3 equations and 3 unknowns, and you solve the equations and substitute back. But don't calculate the answer, just draw it. Just draw the bisector of P and Q. The line PQ, which is all the points equidistant from P and Q. The same for Q and R, okay? And where those 2 points intersect, that's the center of your circle. That's the only point that's equidistant from the three points. So you didn't have to calculate anything. You just draw the 2 lines, and where they cross, that's your answer. That's the circle. The end. And how do you draw bisectors? With a straight edge and compass, okay? And how do you write the code? Well, the code in the blue box just says what I've been saying in English. Let PQ be the bisector of P and Q, and so on and so forth. Let C be the intersect of PQ and QR, and make a circle whose center is C and whose radius is the distance from C to P. So you've just got a programmable straight edge and compass, and with this, you can design a cello, traditionally. So with the CT data for the CT data from this instrument and some nice photographs, I produced this drawing on the right. The drawing on the right reiterates the kind of things I was showing you for the violin. And from that drawing, I massaged it a little bit to make what's called an internal form, which is the standard Cremonese way of making stringed instruments. I printed out this drawing full size and slapped it on some birch veneer plywood, cut it out in a bandsaw, made 2 copies, and that's my internal mold for the cello. And the brown blocks that you see there are the corner blocks that go in they're going to be part of the cello. They're trimmed to shape, and it's the ribs that get glued to them. So here's the ribs having gotten bent and glued onto the blocks. And there's one more thing I should tell you, that I made a proportionally reduced cello, that I didn't make a cello like the original cello, because the original cello, and this is the original cello, has what's called a body stop of 417 millimeters. That's the distance from here to the nick in the middle of the F hole. And 417 millimeters is too big. The design of the cello hadn't standardized at the point that this cello was made. Imagine if I asked the pianist who's going to play today, would you play this piano, but the octaves are 1/2 an inch wider? The pianist would say, I'm too worried about my fingers, I won't do it, okay? So I wanted to make a cello. I liked the geometry of this cello, but I didn't like the dimensions of the cello. So I proportionally reduced it to have a body stop of 400 millimeters, which is closer to the modern standard. And so the cello that I made is actually a smaller version of this, but it's dimensionally, but like the modern instruments. And Stradivari's cellos evolved towards the standard that's accepted nowadays. And this earlier cello, proportionally reduced, is like those more modern instruments. And it's circumstantial evidence that he knew something about proportional design. And in addition, Alessandro Capra, who was a family relation, was an architect and mathematician who wrote a book including chapters on geometry and proportions. So he was in a milieu where he could have soaked stuff like that up. So I put out all this information about this instrument, and there's a series of modern makers who are now making copies of this instrument, and there may be more who I don't know about. My friend Kevin Kelly, who's a violin maker in Boston, has used the software to do what I call computational art history. So this is like a family tree where the square black lines are literally, father and son, and the other ones, the diagonal ones, are apprentices, possibly. Okay? So what Kevin did was he wrote code for a violin by Andrea Amati and then said, how do I have to tweak the code to get the violins further down in the food chain? You can almost imagine the apprentices saying, how did you make that new model violin? He goes, well, at the point where you do this part in the design, I did this instead. Okay? So the code becomes a way of communicating ideas about design. And it's an important lesson for computer science that code is not only to tell machines what to do, it's for people to communicate ideas to each other, properly written. Okay, and there's a YouTube video about this. Okay, finally, I'm doing good on time. I wanted to talk a little bit about arching, because the outline of the instrument is purely two-dimensional. How could you talk about arching? So I'm not the first one to think about this. There was an article by François Denis called Golden Arches, with an obvious hamburger aside, that looked at cathedral arches as a model for the arching on the front and back of instruments. This is another famous article about curtailed cycloids, which are, if you ever knew the child's toy spirograph, that's what curtailed cycloids are. And then there's this website called MaestroNet where people just jabber endlessly about this kind of stuff, on and on and on and on. So, when you're given information about a cello that you'd like to make, most often when you're told about the arching, you're given some templates that are called the quinta, the 5, and you can see them in red there. Okay? You're given the cross sections of the arching at those 5 critical points, and you're supposed to blend the wood in between the arching information that you're given. Okay? And these are some famous templates that are in the museum in Cremona. But the cardinal rule of my life is to try not to screw up, especially with a really expensive piece of wood. Okay? And so what I wanted to do was code all the cross sections, all of them, not 5 of them. I wanted to code all of them. I wanted to have the topographical map that you can see on the right. I wanted to know the points of inflection. I wanted to know everything before I got a gouge anywhere near a piece of wood. Because good tone wood is really expensive. And designing and arching is a reversible process, but cutting wood is not. No matter how many times you cut a piece of wood, you can't make it bigger. So I decided, try and derive the surface, the 3D surface, from some 2D curves. I wanted to do this in the simplest possible way. Even if no one in the Renaissance did it, I wanted to do it in a way that someone in the Renaissance could have done it. So what I did was I began with 3 blue 2D curves. And you can see so it's curve number 1, number 2, and number 3. And number 1 looks like a guitar. It looks like the outline of the cello without the corners. Everybody see where that is? And then in the middle is the long arch. So that's the arch that's going like from here to here. That's curve number 2. And curve number 3 is sort of the points of inflection. And I drew them all on one plane. They're not really the points of inflection, but you'll see what it does in a sec. So every time you do a cross section through this drawing, you get 5 points. You get 2 points on the left and 2 points on the right, and then the height in the middle, okay? And all I did, I just fit a circle to the 3 points in the middle, and then I made a big circle that was sitting exactly on the outer points, and I just increased its radius enough that it would be tangent to that part in the middle. And that's how I made the archings, okay? So if I said points of inflection, sort of, it's the blue points that are the points of inflection between the convex and the concave. Got it? So the blue points mark the points of inflection. And then when I compared my iso heights to this famous book by Simone Sacconi, they looked pretty much the same. I was doing pretty much the right thing. And I have other sanity checks to make sure that I wasn't screwing up that I don't have time to talk about, but that's enough for now, okay? So that's how I did the arching. And I could draw all the points of inflection. There you see the points of inflection, and I got what I really wanted in the middle. I wanted to have a slightly increasing barrel that was just circular through the middle of the instrument. So I got what I was looking for. And I won't describe how, but it's a very easy straight edge and compass construction to do this, okay? So it's something that someone in the Renaissance could have done, even though I haven't a shred of circumstantial evidence to say that anyone ever did, okay? So then I printed out a full set of, a full-size print of all of these templates, mounted them on 1 millimeter ply, and used them to cut out the top and bottom of the instrument with a gouge and planes and everything. And what I had pretty much done, without really intending it, was I had designed an entire tool path that could have been used for a 3D printer to print the arching, or for a CNC router to cut the arching, because you go up the hill and down the hill, and move over and go up the hill and down the hill, and move over, okay? So I started messing around with the CNC machine, but it's not fun. It was boring. You just load in the data, and then you just check, 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 press the button, hope nothing goes wrong. It's more fun to use hand tools. So I've stopped doing that. And at the base of this whole thing is this database, which I want to go online this summer. And I'm still negotiating with people about various stuff. I'm hoping soon to have the CT data for a Brothers Amati cello. That's quite exciting to me. I talk about the acquisition of data the way museum curators talk about the acquisition of instruments, you know. So, and yeah. So, time to wrap up. This movie that I loved about Tim Jennison, who painted The Music Lesson. He's talking to David Hawkins, and he said, there's this modern idea that art and technology must never meet. You go to school for technology or you go to school for art, but never for both. But in the golden age, they were one and the same thing. People just wanted to do better, and what they could do to do better, that's what they did. It's a great idea. And this is me and Tim. I got to meet him in San Antonio this winter. Some thank yous. First, to the curators and museum directors who helped me, Paolo Bodini, Carlo Chiesa, and Arian Sheets. I'd be gonzo without them. They were fantastic. My technical gurus have been great, particularly Misha Pivovarov at the Harvard Medical School Systems Biology Lab. Even went to Cremona to see the cello I'm obsessed by. And my violin buddies are the top. Absolutely the tops. Curtis Bryant, my tango dancing friend, has been a big brother and Sherpa guiding me up the Lutherie learning curve. Francois Denis' book and personal explanations made this part of my life possible. And Michaela Dobner is a great Cremonese luthier and an even greater human being. So we went cycling in Tuscany 2 years ago. Entering Siena was just stupendous. And I have in my notes, if Radcliffe Fellow Rob Vircha can go snorkeling in Polynesia while doing research, I can do this. Okay? And now, instead of Q&A, we're going to have some music. Leonard Bernstein's Norton lectures at Harvard were called The Unanswered Question. I'll answer your questions by email and at lunch today for those of you who are here. And we also have a concert demonstration of the tech stand, an innovation of our multi-talented cellist today, Emmanuel Feldman, allowing him and all cellists to play standing up. But here's some brief explanation about the first piece. Lisa Cristiani was a Parisian cello prodigy and likely the first woman to achieve success as a cello soloist. In 1845, at age 18, she gave a concert in Leipzig where her pianist turned out to be Felix Mendelssohn. Clearly taken with the musical encounter, he promptly wrote and dedicated to Lisa his well-known romance, The Song Without Words, the first piece we'll hear. See the original manuscript up on the top. Dédié à Mademoiselle Lisa Cristiani! Exclamation point. Her Stradivari cello is now the jewel of the collection at the Museo del Violino in Cremona, the cello whose beauty beguiled me. And it's a lovely moment to conclude this presentation and this year's public presentations. Please welcome Emmanuel Feldman, who will play my recently completed version of Lisa Cristiani's famous and remarkable cello in collaboration with pianist Anne Tyson.
Thank you, Anne and Emmanuel, for this wonderful gift. Thank you so much. Thank you, Harry, for your inspiring presentation and for organizing this for us. I want to thank the audience here in the room with me and online. Thank you for attending. As Harry mentioned, this is the last of our Fellows Public Talk this year. We will return in September. However, Radcliffe programming continues over the summer. You can find out about Radcliffe public programming at radcliffe.harvard.edu, where you can also watch videos of past events. Thank you very much for joining us throughout the year. Have a great rest of the day.